Hi, as our course is named Probability Theory and Mathematical Statistics, so it consists of two parts of the probability theory and the mathematical statistics. And today we start the second part. So all we dealt with up to our today's lecture were probability theory, and now we'll start with the mathematical statistics. Actually, mathematical statistics is solving two types of problems. I would say that maybe 95% of all problems that are solved by mathematical statistics are of some of these two types. And these are problem of estimation and hypothesis testing. So each problem is either estimation problem or the hypothesis testing problem. And today I'll try to explain you what the estimation problem is and what an estimator is. And our first topic is point estimators. So what is actually the problem? An unknown parameter estimation problem. Let me explain with the example I have already told you. So you need to measure the length of a table. To measure it to within 1 millimeter, so with high accuracy. But you don't have a measuring tape. You have only a short ruler. And so the only way to measure this length is to attach this ruler several times, and this kind of measurement gives you an error of plus minus 6 millimeters. So this is not accurate, not enough accurate for you. So what to do? How can we solve this problem? How can we avoid these big errors, unacceptable errors? So the natural way to do so is to do this measurement several times, many times. If you want high accuracy of measurement, let's say 100 times, and then calculate the arithmetical mean of these measurements. So you measure the table length 100 times, you get 100 numbers, and then you calculate the arithmetical mean of these numbers, and you say that this is what I assume to be the table length. What we do here is solving an estimation problem. And in this problem, there are, how to say, three characters. The first one is the unknown parameter. In our example, the table length is an unknown parameter. And you should know that it is non-random. So an unknown parameter is not a random variable. Why? Because it does not depend on the outcome of any experiment. So the table length is always the same. The table is the same. Its length is equal to some number, to a certain number. We just don't know this number. So it is unknown, but it is not random. Then the second character is the sample or observations. So in this example, results of our measurements are observations. The result of each single measurement is one observation. So observations are random variables, as they are unpredictable. So each observation is actually a real length of the table plus a random error, and so the value of this error it is unpredictable. So this error can take any value in some range each time you do this measurement, each time you are measuring the length. So observations are random variables. And then the result of our operations on observations is an estimator. So in our example, this arithmetical mean of measurements is an estimator of an unknown parameter based on observations. So in other words, we can say that an estimator is a function of observations. So in our case, this function is the arithmetic mean. So as observations are random variables and the estimator is a function of observations, then the estimator also is a random variable. So it is a function of other random variables. And really, so each time you will repeat this big experiment. So the experiment is measuring this length 100 times and then calculating the arithmetic mean of measurements. So each time you do this, you'll get different numbers, slightly different, but still different. So this means that each time the experiment is repeated, we get the different numerical value. So that means that we have a random variable. So we have an unknown parameter, we have observations, and we have an estimator of the parameter based on observations. And the parameter is a non-random number, non-random but unknown number. Observations are random variables, and the estimator is also a random variable. Now, let's try to define this mathematically. But before the definition of an estimator, let's talk a little bit about what we call sample in our science. So previously, I used the term observations, but usually in mathematical statistics, we don't say observations, but we usually prefer to call them collectively, to call them a sample. So a sample of the signs n is a set of n independent, identically distributed random variables. So we say that observations are independent from each other. And we say that they are done according to the same scheme, according to the same rule. So observations are identical. That is why random variables we observe each time the observation is done are identically distributed. So just in practice, the sample is the result of our observations. So the sample is what we observed. And in mathematical sense, so a sample is a set of n independent, identically distributed random variables. So we can say that this is a set of, actually, we can say that it is a set of several random variables. But we can also look at this like kind of several observations on the single random variable. So, for example, I can say that if I go out to the street and measure the height of the first person I meet there, this is a random variable. So the height of the first person I meet at the street. And if I do this several times, for example, if I measure the heights of first 20 people I will meet there, so these are, I can say that these are 20 independent random variables. So x1 is the height of the first person I will meet, x2 is the height of the second one, and so on. So I have 20 independent, identically distributed random variables. But from the other hand, I can say that this is just a single random variable, so the height of the random person, and I observe this random variable 20 times. For some technical mathematical reasons, we prefer to say that we have 20 random variables, not that we are observing a single variable 20 times, but that we have 20 random variables. But in practice, actually, these 20 variables are just clones, so they are identical. After we know what the sample is, let's mathematically define what an estimator is. So let the distribution law of the sample elements be known up to an unknown parameter. So there is a parameter theta, and so this theta is unknown, but in general the distribution law of x's of the observations of the sample is known. For example, we can say that observations follow normal distribution with parameters 0 and theta. So one parameter is given and the other one is unknown. And so, in such a situation, a point estimator of the parameter theta based on a sample, x1, xn, is a random variable that is a function of the sample and takes values from the set of valid values of the parameter. So, the standard conventional way to denote an estimator in statistics is hat over the letter. So if the parameter itself is theta, then theta hat is an estimator of this parameter. And index n is sometimes used to show the sample size. So to let us know what is the size of the sample. So how many observations we consider to estimate this parameter. So and so you can see that the estimator theta hat is a function of the sample. So it is equal to phi of x1, xn. So this is the definition. But if we try to understand this definition, we can see that actually it is, how to say, not so very informative. So, according to this definition, some very, how to say, stupid estimators can be called estimators according to this definition. For example, let's imagine that you have measured the length of your table 100 times, and you have these 100 numbers written down on a sheet of paper, but you don't know the mathematical statistics. You have not studied the mathematical statistics yet, and you go to me and you ask me, could you help us please to estimate the real length of the table basing on these observations? And you give me this sheet of paper and you ask me to estimate the length of your table. And I tell you, so 150. You say, what? I say 150 centimeters. This is my estimator of the length of your table. And you say, sorry, but you didn't have even a single look at the numbers I have given to you. So you didn't look at this at my sheet of paper. You didn't do any calculations, and you tell me the result. You tell me the number. So how this is possible? And I can tell you. So look at the definition of what an estimator is. So they say that estimator is a function of observations, function of the sample. So my function of your sample, of your observations, is just a constant. So my function is equal to 150 for any values of its arguments. So my function is a function of 100 arguments, and it is equal to 150 always. So it is a possible situation, for example, f of x is equal to 3. So the function such that its graph is just a horizontal line. So this can be applied to a function of several arguments also. So this is my function. And so what do they say also? They say that it takes values from the set of valid values of the parameter. So the parameter is a table length. So table length, what are acceptable valid values of the table length? So positive numbers. So the number I told you is positive 150, not minus 150. So this is my estimator. This is an estimator according to this definition. So that means that, but you understand that this is so this definition is not so very, how to say, so very clever. So this definition so don't help us to divide estimators that can be applied for estimation of something from the estimators that are actually something just stupid, like the example I have just given. So this estimator, to just every time to say the same number, this is not a clever estimator. So it shouldn't be used in real life, but it is an estimator. So besides the definition, we need some additional properties that will help us to understand which estimator is good one and which is the bad one. So which can be applied and which cannot be applied for solving an estimation problem. So let's now discuss these properties. The first is what we call an unbiasedness of an estimator. So an estimator is called unbiased if its expected value is equal to the parameter we are estimating. So theta is the parameter, theta hat is an estimator, and if E of theta hat is equal to theta, then we say that this estimator is an unbiased one. So what does it mean? It means that there is no systematic error, systematic overestimation or underestimation. So if, for example, if we measure the table length 100 times and then calculate the arithmetic mean of these measurements, and so we see that we get the number that is more than the real, greater than the real table length more often. So, for example, in 60% of cases, we get a number that is more than the real table length. This means that this estimator systematically overestimates the parameter. So it is not an unbiased one. And so an unbiased estimator is such that there is no overestimation and no underestimation, so that estimator average mean value of an estimator is equal to the parameter we are estimating. So the second important property, probably the most important property that every good estimator must have is a consistency. So an estimator is called consistent if the sequence of estimators converges to the estimated parameter when n tends to infinity, converges in probability. So what does it mean? It means that the more observations you have, the more accurate the estimator is. So that, for example, if you measure the length of your table with a ruler 20 times and then calculate the arithmetic mean, this estimator will be more accurate than if you do this just 10 times. And if you do this 50 times, this is better. And if you do this 100 times, it is even better, and so on. So when you increase the number of observations, you also increase the accuracy of estimation. This is what the consistency is. So consistency means that you can get as accurate estimator as you wish if you can make as many observations as you will need. So, and if you have, let's say that you have several different estimators for the one single parameter, and they are all unbiased and they are all consistent. And so which one is the best one? How to choose? So, for example, you have several ways to estimate one parameter, several formulas. So this theta 1 hat is calculated according to this formula, and theta 2 hat according to this formula. And so how to choose the best one? So how this can be done? So how can we introduce several different estimators for a single parameter? Let's imagine an example. It's a little bit maybe stupid one, but easily understandable. So let's say that the first estimator is when I calculate the arithmetic mean of my observations of measurements. So I measure the table length 100 times and then calculate the arithmetic mean. So this is the first estimator. And the second estimator is when I choose only measurements with odd numbers. So I choose only the first, the third, the fifth, the seventh, and so on. I choose only half of measurements and then calculate the arithmetic mean. So this will also give me an estimator, a valid estimator that is also unbiased and also consistent. It is a stupid estimator, as it's just we refuse to use half of measurements. It is not a clever step to do so, a clever decision, but still, so it is possible to apply such an estimator also. So how we can compare them? If we have two estimators that both are unbiased and consistent, how can we compare? How can we choose which one is the best one? So the best one is the most accurate one. And what do we mean saying accurate? So we are estimating an unknown parameter. What do we mean saying an accurate estimator? Accurate means close to the real value of the parameter. So if the difference between the estimator, the random value of the estimator, and the parameter is little, if the difference is small, so then we say that this is an accurate estimator. If the difference is high, so we say that this is a bad estimator. This estimator is not so very accurate. So accuracy means difference between the estimator and the estimated parameter. But the estimator is a random variable, so the difference is different each time we do the experiment. And so if the estimator is an unbiased estimator, then the expected value is equal to the parameter we are estimating. So deviation of an estimator from the parameter, from the estimated parameter, is at the same time its deviation from its own expected value. And so what property, what feature of a random variable shows us how big its deviation from its own expected value is. This is the variance. So if we have several unbiased estimators, the one that is called an efficient or an effective estimator is the one that has the minimum possible variance. So the less the variance is, the more accurate estimator is. So efficiency or effectiveness, these terms are synonyms, is the highest accuracy compared to all other estimators. So the best one is the efficient one. The efficient one is the one with the minimal possible variance. So when someone suggests a way to estimate an unknown parameter, if one tells, let us do this according to this formula, let us calculate the estimator with this formula, we can just check if this estimator is an unbiased one, is a consistent one, and is an efficient one. So, and the most important of these three properties is the consistency. So, if the estimator is consistent, it is not so very big problem if it is not unbiased, if it is a biased estimator, for example. Let me just give you an example. You have, let's imagine, an ideal bus line, so such that buses depart from the bus stop every 5 minutes. So the interval between buses is fixed. Every 5 minutes, the bus is departing. And let's imagine that you have the bus stop of such an ideal bus line near your house, but you don't know the interval. You simply know that there is a fixed interval between buses, but you don't know its value, its length. And you can easily measure this interval if you just miss one bus and just measure how long will you wait for the next one. But you are always in hurry. It is impossible for you to do so. So you always take the first bus that comes to the bus stop. And so to estimate an unknown interval between the buses, every time you are waiting for the bus, you are measuring the waiting time. So, for example, today I waited 3 minutes and 15 seconds. And so next day I will wait for 32 seconds, next day for 3 minutes and so 52 seconds and so on. So, and you do so, let's say, for 100 days. So you have 100 waiting times, and you are trying to estimate an unknown interval between the buses using this sample, using this set of observations, 100 observations. So how this can be done? What is the most natural way to do so? I would say to take the maximal number, maximal observations, the longest waiting time as an estimator. So it is a consistent estimator, as so the more number of observations is, so the closer this maximal value will be to the interval between the buses. So if you are using this bus line for several years, for example, there will be such a situation that you come to the bus stop just several seconds after the bus departed. And so waiting time will be almost equal to the interval between the buses. So the natural estimator to estimate an unknown interval between the buses is a maximal element of the sample, the longest waiting time. And this estimator is a consistent one, but it is biased. It is always underestimating the real interval time between the buses. So as it is always less than the real value of the interval. Waiting time is always less than the parameter you are going to estimate. So this estimator is a biased one, but it is consistent, so it can be applied, it can be used. So I told you that an estimator can be unbiased. So unbiased means that there is no bias. So that means that there is a thing called bias. And yes, there is. So what is a bias? Bias is a mean difference between the estimator and the parameter that is estimated. So bias of theta hat is defined as expected value of theta hat minus theta. And as theta is non-random, theta hat is a random variable and theta is a non-random parameter, so this is equal to E of theta hat minus theta. So this is a bias, and so we can say that estimator is unbiased when the bias is equal to 0. So when the bias is 0, then E of theta hat is equal to theta. What we saw in the definition of an unbiased estimator. Then, if the estimator is an unbiased one, we can measure its accuracy with the variance. But in general, for both biased and unbiased estimators, the general measure of accuracy is the mean square error. So the mean square error is defined as average squared difference between the estimator and the parameter we are estimating. So the bias is the average difference and the mean square error is the average squared difference. And so we know that variance of a random variable is equal to the expected value of x squared minus squared expected value of x. And so we can use this formula to derive another expression for the MSE that is more convenient to use. So we can prove that MSE is equal to the squared bias plus variance of an estimator. So this means that for unbiased estimators, for such estimators that their bias is 0, MSE is equal to the variance. And for biased estimators, so MSE is equal to the variance plus a squared bias. So this is the formula we are usually using to find MSE when analyzing and comparing different estimators.